Today we're going to be talking about section 3 of our textbook, which covers trigonometric integrals. Really what it is today we're going to be dealing with integrals that have to do all with trigonometry. We're going to be using either identities or these rules that I will provide for you, and then identities to help you solve those integrals. Cool? We're going to divide this up into sections. First we're going to talk about sine and cosine, and then we'll move on and talk about cosecant, cotangent, secant and tangent, etc., etc. Cool? So we'll start out with the more basic and the more simple ones to deal with, which is sine and cosine. So there are three scenarios you're going to deal with here. I've already written them here, so if you're watching the video, just go ahead and pause the video, write down the rules. And if you're in class, I'm going to do the same thing. I'm going to pause the video, write down the rules. We'll use the rules and we'll solve some integrals with sines and cosines. Okay, at this point, I'm assuming you've already have the rules down. So it really just comes down to practice. The more you practice this, the more patterns you see and the easier this becomes. Okay, so the very first example that I have for you is going to be this one right here. So we're going to integrate sine to the third power of x times cosine to the fourth power of x dx. Now, this is a little different than the type of trig you've encountered before, because in the past you were able to use u substitution, like selecting sine being u, you knew that the derivative was cosine. But because that cosine has a fourth power, u sub is no longer going to help us. And vice versa, choosing u to be cosine, we have a derivative of negative sine, but because the sine has a power of 3, we're not able to use u substitution. That's the problem. Cool? So we're going to basically, you don't have this memorized yet, so you got to look up at your rules and see which one would apply in this scenario. So we've got, it says, if the power of sine is odd and positive, which with that, we have that going on, according to the suggestion of how to solve this problem, is to save one of your sine factors. So in other words, you've got to rewrite this. Instead of saying sine to the third power x, you are going to say sine to the power of x times sine squared to the sine square of x, times cosine to the fourth power of x dx. Now, I'm going to show more steps than I usually would, just so that you understand what is happening. You're going to go back to use your trig identities from trigonometry, and this can be substituted by what? Okay, so we're going to make that substitution. We're going to have sine of x times 1 minus cosine square x times cosine to the fourth power x. And we're just going to multiply everything out. So now it's just algebra. Yes, so we've got the integral of what? We've got that times that gives you sine x cosine fourth power of x. And then that times that gives you minus sine x cosine to the power of 6x dx. And by doing so, what do you notice? Now u substitution comes into play. Okay? We can let u be what? Cosine. We definitely do not want to make u the sine. Yes, we want to make u the one with the power. Yes? So the one with the power on both of this is cosine, so we're going to let u be cosine. So u equals to cosine of x, which means that du is equal to what? Negative sine x dx. Now, I don't have a negative with this one, so I'll fix this one in a second. But this one already has a negative, right? So I'll be able to take care of that, right? So what is the integral here? Well, if we use u substitution, I'm not going to show all the work. We know that this technically just became u to the fourth power, right? If I integrate that, that gives you u to the fifth over 5. With a negative up front because I need a negative. Agreed? So this right here becomes negative what? Cosine to the fifth power over 5. And then this one right here just became u to the sixth, right? Positive because it already has the negative in there. Agreed? So if we integrate that, what does that give us? U to the 7 over 7, which in this case would be cosine to the 7 over 7 plus c. And that would be the solution to our integral. Okay? So we're basically let's summarize what happened here. you're going to use the rules above to rewrite it in a way that you can use U substitution. That's really what's happening here. Cool? You're going to use identities. You got to find a way to use identities so that U substitution works. Cool? Questions about that? Yes, ma'am. Why did I pick the sine versus the cosine? Because that's a great question. So here's what happens. If you have an odd power, notice how the first rule and the second rule says that it's odd and positive. If you have an odd power and you keep one, that means that the remainder are going to be an even power. And trigonometric identities, the Pythagorean identities, are dealing with even powers. So that's why we're going to be able to rewrite it. That's the reason why I chose the sine, because the sine had an odd power. So keeping one of them will cause me to have an even power remaining factors, which I can then use Pythagorean identities to turn into cosines in this case. Oh, no. You just basically see which scenario applies. And sometimes there are going to be scenarios where multiple of them will apply. You just choose one and hope for the best, honestly. Cool? I mean, you honestly would not know where it's going to take you until you start actually working with it. Cool? All right, do we get the idea of what's happening? Yes? All right, let's try another one. So I'm going to let you try this on your own. So we're going to do a definite integral to make sure that we don't forget how to use our fundamental theorem of calculus. So we're going to do a definite integral from pi over 6 to pi over 3. And I'm going to throw a curveball your way, see if you guys can handle it. So cosine of the third power of x divided by the square root of sine of x dx. I will tell you that this is not going to turn out to be pretty, but I want you to give it a shot. You have the rules, okay? See which one of the rules apply, and then just proceed from there. Cool? So if you're watching the video, I'm going to go ahead and tell you to pause it, give it a try, and then when you're ready, hit play again. All right, I am assuming you've given it a go. So here's what I got. Let's talk about the calculus part of it because the algebra was terrible, right? And honestly, I didn't even simplify. I would just left it wherever I put it here on the paper. But anyways, first, you should have recognized that we had an odd power of cosine, which meant you were supposed to keep one cosine and convert the other one to cosine squared in this case. Cosine squared is the same thing as 1 minus sine squared. Yes? So I can rewrite it. I kind of rewrote it this way. Maybe it helps you out. Yes, I'm going to keep that cosine by itself. I'm going to actually do the division here, 1 over that, and then sine squared over that, which breaks up into those two expressions there. If you multiply in the cosine, then you can actually break it up into two separate integrals. You do not have to show that you broke it up into two integrals, but if you wanted to, you could. We're going to let u substitution here, and we're going to let u be sine. Yes? And you should be able, calculus-wise, to get that this was 2 square root of sine, or 2 sine to the 1/2. And the other part of it would have been negative 2/5 sine to the 5/2 power. Cool? And then this is a definite integral, so you were evaluating both of those from pi over 6 to pi over 3. I wouldn't take it any further than that, honestly. I'm not going to give you anything with this numbers that difficult on an exam. If I did, I would let you use the calculator to figure that out at that point. Cool? Yes, sir.
So when you brought the sine to the 1/2 x up, you multiplied the 1 minus sine squared x.
Right here.
Why is the minus sine x? Is it 2 over 2 or 1?
It's 3 over 2. So right here, so think about it. 1 over sine to the 1/2 x, you understand why it's sine to negative 1/2 x, right? But when you have sine divided by sine, because it's the same base, all you got to do is subtract the powers. So 2 minus 1/2 is 3/2. Cool? Any other questions? We're good? All right. Then let's move on to our next problem. So let's say that we have something like integral of cosine to the 4th power of x dx, completely by itself. Cool? All right, so this is where that third rule kind of comes in and helps you out. It says that if you have even powers, you are going to use the power reducing identities. Okay? First of all, what I would do if I were you is I would rewrite this in a manner that I had a cosine square. So in this case, that would be a cosine square x squared dx. Now this is where you want to be careful. I know that cosine square x can be replaced with 1 minus sine square x. Yes? And that you could square that. Agreed? But wouldn't that lead you to also having a sine squared? And then at that point, you're going to be like, well, let me replace that with cosine squared. And then you're going to find yourself in a loop and never going to answer the question. So the reason why I'm not replacing this with the Pythagorean identity is because I don't have a sine next to it. You with me? I only have cosines, which means that I have to use the power reducing identities. Cool? So the power reducing identity for cosine square, it is equal to 1 plus cosine 2x divided by 2 squared dx. And you will have to know those for the tests. Cool? So there's a power reducing. What do you suggest from here? Anybody? Something. What would you let u be? The 2x. Now we got to be careful about that. Are you saying that because then that 2 can kind of go away? You got to be careful because in technicality that's a 1/2. You see what I'm saying? So, but then even if we got rid of that, then our problem would still be that 1, and then that would still square. Cool? So I don't think u substitution would be the way to go here. I think you just forget calculus. I think you just need to go back to algebra. Like, what do you need to do? Like, not factor it out, but the opposite. Multiply it all out and see where it takes you. So we're going to go ahead and multiply everything out. So what do I have, or what do I get if I multiply 1 plus cosine 2x over 2 with itself? 1 plus 2 cosines 2x plus cosine squared 2x over 4 dx, right? Okay, but now what? Say that one more time. Well, there's a couple things I can do. First, I can get rid of, well, not get rid of, but I can pull out a what? I can pull out a 1/4. Secondly, I can split this up into 3 different integrals. You don't have to, but I'm kind of just trying to show you, because 2 of these I'm ready to solve. One of them is the one that's giving me trouble. But I can separate this into 1/4 1 dx plus 1/4 integral 2 cosine 2x dx plus 1/4 integral of, what do I got, cosine squared 2x dx. Out of these 3 integrals, you can solve 2 now. The last one, we'll talk about it here in just a second. Okay, so what is the integral of this? X, so it'll just be x over 4. Cool. I know it has a plus c, but we'll tackle the plus c at the end. Cool. What about this? Well, I can do u sub, where u is 2x, which means that du would be the 2. So in reality, all I have here is cosine of u, right? If I replace this with a du, right? So what is the integral of cosine of u? Sine of u, right? But I have a 1/4 outside, right? So it's going to be plus 1/4 sine of u, which in our case is 2x. Agreed? And lastly, I'll go ahead and rewrite it again, but how could we tackle that problem? Say that one more time. Good. You have a cosine square again. You're going to have to power reduce it again because I don't have a sine again. You with me? So I'm going to have to power reduce it. But here's the difference. At the beginning of the problem, we had a cosine square of x. Now we have a cosine square of 2x. Does that make a change to the power reducing formula. Because the power reducing says cosine square of x is equal to 1 plus cosine 2x over 2, right? What would happen if I have a cosine squared 2x? 1 plus cosine, why is it a 4x? Bless you. Think this through, guys. If I have an x here, then that means I have an x there. So if I have a 2x here, that means I have a 2x there. 2x times 2 gives you the 4. Yes? That's the reason why. So what would it be if I had cosine squared 3x? 1 plus cosine 6x over 2. Cool? Alright, so now that I know what I need to change it to, kind of wrote all over it, I'm going to go to the side. I have a 1/4 integral of 1 plus cosine 4x over 2 dx. I can pull out a 1/2, right? So that would be a 1/8. Bless you. 1 plus cosine 4x dx, right? Okay, what is the integral of 1? What is the integral of cosine 4x? 1/4, positive or negative? Positive, right? So 1/4 sine 4x plus c, right? Now, let's not get lost. It was that part plus this part right here, right? So final answer, let's see, I have a 1/8 x, right? Which I can combine with this x to the 4th, which would be 3/8, right? So 3/8 x. And then this and this wouldn't combine, right? So plus 1/4 sine 2x plus 1/8 times 1/4 would be 1 over 32 sine 4x plus c. Cool? Alright, questions about sines and cosines? Sure? Okay. I mean, obviously we can practice more, but you can practice the rest of this on the homework. Cool. Now we're ready to move on to secants and tangents. And there are 5 rules for that. So, 5 rules. It's not the best handwriting, but here we go. Okay, so we're dealing with secant and tangent. Number 1, it says that if the power of secant is even and positive, then we're going to save a secant squared and convert the remaining to tangents. The reason why we want to save a secant squared is because of the trigonometric identity, tangent squared plus 1 equals secant squared. You with me? Okay. I'm going to talk about them and I'll let you write them. Number 2 is if the power of tangent is odd and positive, we're going to keep a secant tangent. Now, this is assuming that whatever you're integrating also has secants with it. So if you have something that has secants and then it has a tangent that its power is odd and positive, then you're going to save a secant tangent and convert the remaining to secants. If you don't have any secant factors, in other words, if you only have a power of tangent and the power happens to be even a positive, you will convert the tangent square factor to secant square factors. Number 4, if you only have secants and to a power and that power is odd and positive, you will use integration by parts. And 5, my least favorite of them all, and the one that you wish that doesn't happen, is that if none of the above work, you will turn everything into sines and cosines, and then you will utilize the 3 rules that we started with today. That is the worst case scenario. You do not want to start there just because you feel comfortable with sines and cosines. I know, like, for example, this is comparable to when you were in trig and you were doing proofs of identities. And like most students felt comfortable with sine and cosine, so they started turning everything into sine and cosines, and typically those proofs turn to be a nightmare? That's the equivalent here. You do not want to go to sines and cosines unless you don't have another option. Cool? So I'll go ahead and pause the video, let you write this down, and then we'll continue. Alright, I'm assuming you've written down the rules, so we're ready to try out an example. So, let's do our first example for this. Let's do an integral of secant to the power of 4, 3x, tangent to the power of 3, 3x dx. Okay, so the rules are a little differently this time, right? So go back and read the 5 rules that I provided, and let's see which ones would apply, if any. So the first one applies, right? We have a power of secant being even, right? So we can use that one. Could we use the second? It says the power of tangent is odd, right? So we could use the second one as well. Now you don't want to use them both. You gotta pick one and go with that and see where it takes you, right? The third one doesn't apply, right? There are secant factors. The fourth one doesn't apply because there is a tangent factor. And we said the fifth one we're going to avoid if possible. Yes? So you've got a choice here, and you've got a choice to make. Where do you want to go with this? First one? Okay, so you've chosen the first one, which means that we are going to keep what? One of the secant squares. So we're going to keep one of the secant squares, which means that I have secant squared 3x, tangent cubed 3x dx, right? So what are you going to do with the other secant square? Turn it into tangent squared 3x plus 1 in this case, right? So we're going to keep 1. This one becomes tangent squared 3x plus 1 times the tangent cubed 3x dx. Once you do that, the rest of this should start cleaning up pretty nicely. Okay, which means we just have to multiply, just got to do some arithmetic, and things should start looking better. Okay, cool. So what happens when I start multiplying this in? So I've got that times that times that, which becomes what? Secant squared 3x, tangent to the 5th power 3x, and then I've got that times that times that, plus secant squared 3x, tangent cubed 3x dx, right? So this entire thing dx. Bless you. Do you guys see it? What is u? Tangent, because the derivative of tangent is secant square, and that is the reason why we wanted to keep a secant square. Now you gotta be careful because this one has a 3x, so therefore we need a 1/3. Yes? So that means that the integral for this part is what? I need a 1/3. This would be like saying u to the 5th, so this would be u to the 6th. So tangent to the 6th power 3x over 6, right? Same idea here, right? You've got the exact same thing going on here, except we need a 1/3, right? And this time it's u to the 3rd, so it would be tangent to the 4th 3x over 4 plus c. So final answer, if I clean this up, would be what? Tangent to the 6th power 3x over 18 plus tangent to the 4th power 3x over 12 plus c. Cool? It's not as bad as it seems when you're writing all these rules down, right? It really, if you really narrow these rules down, it's just like, how can we make the problems easy enough to use up? I don't know if you've noticed that was the same thing that happened with integration by parts. Like, how can we still use substitution to solve problems? Bless you. Cool. All right. Questions about this one? All right. So I'm going to let you try one on your own, and then we're going to tackle one last one together, and that'll be it for today. So let's take an integral from 0 to pi over 4 of tangent to the 4th power of x dx. So if you're watching the video, go ahead and pause it, give it a shot, and when you're ready to check the answer, hit play. Alright, so for this example, let's just go over it very quickly. I rewrote tangent to the 4th power of x into tangent square x times tangent square x. I turned that tangent square x into secant square x minus 1 and distributed the tangent square so that I could have two separate expressions here. This is a simple u substitution because we know the derivative of tangent is secant squared, so it's a u sub. So this would be u to the 3rd over 3, which gets us to this part. Now this part is where you got to think about it a little bit. Instead of, I don't know, like if you going back and thinking of everything like other rules, you got to remember like tangent square x is the same thing as secant square x minus 1, but because it's a minus here, that makes this into a negative and that into a positive. And that's simple to integrate because the integral of secant square would be tangent, which gives us that, and then the integral of x would be that. Evaluate everything at pi over 4. Hopefully we didn't forget our unit circle. Tangent of pi over 4 is 1 to the 3rd power is 1 divided by 3 is 1/3. Minus 1 gets you this negative 2/3 plus the pi over 4. Tangent of 0, 0, 0, 0. So your final answer would be negative 2/3 plus pi over 4. Cool? All right. Any questions about that one? Okay, the last one I want to tackle with you guys would be what if we do like a secant by itself? And let's do a secant to the 3rd power x dx. Cool? So, according to the rules, what do we try? It says integration by parts. But the way you attack this problem, I like that the rule helps you, but it's not very helpful. It doesn't really break it down for you. You're first of all going to rewrite this as secant square x secant x dx. You guys with me? Okay. Now this is where things get interesting because it says we're going to tackle this by integration by parts. But if you realize, according to Liotte, they're both at the same level. They're both trig. So which one's u? And the question then would be, which one is easier to integrate? The secant square. Therefore, we're going to let u be the other thing. You with me? So we're going to say u is secant x, which means that dv is secant square x dx, which means that du is secant x tangent x dx, and then v would be tangent of x. Agreed? So according to integration by parts, we're going to say then that the integral of secant cube x dx is equal to u times v, which is secant tangent, minus this times that, right? So the integral of what? What do we got? Secant x tangent square x dx right? And now what? We're going to go back to our rules. What do we got? So you want to turn this into secant square minus 1? But then what? Because if we turn that into secant square minus 1, right, wouldn't that turn into then secant cubed minus secant? And then what's the integral of secant cubed? Aren't we then back to that? Right? So then, yes sir? I'm sorry? We could convert it to sine and cosines. I don't know that I want to go there yet. But we could, right? I mean, that was an option, right? Sine and cosines. Anything else we could do? It is at this point where I'm like, okay, then if we go back to this, was that the choice then? Like, was that the best choice? Did we choose the right u and the right dv? I'm just trying to think before we go into the sines and cosines. That's all I'm trying to tell you, right? So before we go into sines and cosines, is there maybe, could I attempt something else before I go into sines and cosines, right? Because that's where I'm at currently, right? You guys with me? So the only other thing I could do is to change this, where that's secant, and then that's secant square, right? But I also got to think this through. Do we know the integral of secant? What's the integral of secant? ln of what? Secant x plus tangent x. I don't know that I love where it's taking us, but I'm going to give it a shot before we go into sines and cosines, right? You guys with me? I'm just trying to model to you what I would be doing if I was trying the problem, right? So I tried it, I kind of got stuck, right? Doesn't mean I have to go back to square one. Well, okay, let's see. Let's say we try the different u. So let's say we do u being what? Secant squared x, which means that dv would be secant x dx, right? So then, what would the derivative of u be? Well, this is a chain rule, right? It would be 2 secant of x times the derivative of secant, which is tangent, right? So that would be a secant squared tangent x, right? And then what is this? What is v? Yes? I don't know that I like this one either, but we'll see where it takes us. Alright, so that would be what? That times that, right? So that would be secant square x times the natural log secant x plus tangent x minus that times that. Oof. I do not like that, right? So what's the, I mean, honestly, like at this point, what? Calculator? At this point, it is, I mean, sines and cosines, man, you know? Like, I mean, this, right? Unless, hold on, before, is the derivative of that? Is it? I don't know. Wouldn't that be secant x tangent x plus tangent squared divided by, bless you, secant x plus tangent x? Right? So for this one, no, it's not. No, it's not going to work out. Alright, so sines and cosines? Alright, so here's where we're at. I know like it looks all crazy, but this is the integral we're trying to solve currently, right? Which was, where was it? Secant x tangent square x. Secant square tangent square x. Alright, so where do we want to go from here? Well, integral of is the same thing as 1 over cosine. And this would be the same thing as sine square x over cosine square x dx, right? So technically I have the integral of sine square x over cosine 3x, right? Now if I go back to the original rules of sine and cosine, they both had to do with odd powers, right? If you have an odd power of sine or cosine, you keep one and you turn the remaining into the opposite of it, right? So in this case, we would have to say I have a sine square x, right? I'm going to keep one of the cosines, and then the other one becomes a cosine squared, which is the same thing as what? Right? Okay. Where do you want to proceed from here? Let me rewrite it over here. I run out of space. Okay, so that's where we're currently at. Where do we want to go from here? Do the what? Say that one more time. Uh-huh. Mm-hmm. So you're saying like let u be like one of the signs? Is that what you're saying? I mean, yeah, we could rewrite the other one in terms of u. Like we've done it in the past, right? Remember when we had like u equals x plus 1, which means x equals u minus 1? Is that kind of like what you're talking about? Sure, I mean, we could attempt that. Any other suggestions? Integration by parts. All right, I'm thinking this through. Look, here's where we were at, right? Originally. If I would have turned this into cosines, right? Then I could break it into two fractions maybe and see where it takes me from there, right? Maybe, right? Because this would have been 1 minus cosine squared, which would have been 1 over cosine, which would have been secant cubed. Oh no, but we're back to secant cubed. You guys see that? And then we would have a what? A cosine, so another secant over here. What are we missing? I feel like we're missing something. What am I not thinking of? Right. To the other side, like we did on integration by parts. Is that what we're talking about? Okay, so let's see. So let's scratch this, right? And then we say we're gonna keep it as the cosine was gonna. I mean, what was it on top? The sine squared. We're gonna rewrite it as 1 minus cosine square x over cosine 3x, right? Power 3, which then becomes 1 over cosine, so that'll be a secant cube x minus 1 over cosine, which would be just a secant x dx, right? Okay, so let me kind of back up and rewrite everything we had so we don't get lost. Originally, we started with this, right? We started with secant cube x dx is equal to, and then we did u times v, right? Which got us to, where are we at? Secant x tangent x minus integral of secant x tangent square x dx, right? That's where we started this problem, right? we rewrote that in terms of sines and cosines, right? So we're going to substitute this part with this, right? Do you guys agree? Okay. So we've got secant cube x dx is equal to secant x tangent of x minus secant, oops, I used the integral for my ass. Secant cube x dx, right? Plus, right? Secant x dx. No, because remember, like, when I was simplifying, I ignored that symbol there, so I gotta distribute that symbol. So now what you are saying is to do what? To add this secant to the other side. So that gives you 2 integrals secant cubed x dx is equal to secant x tangent x plus, we know the integral of that, right? What is the integral of secant of x? And what do I have to do then? One half secant x tangent x plus 1/2 ln secant x plus tangent x plus c. There has to be a better way of doing this. I don't know. I mean, we got it, right? Does it make sense? I feel like there has to be an easier way of doing this. Right. But then also, I mean, I don't know if, like, if you're watching this video, I don't know if it was the best way to attack. Like, I know when you watch a video, you kind of want to know the fastest way, but it also kind of hopefully helps you see how, like, you think about the process of a problem, and if you get stuck, how you kind of work around it. Cool? I'll get back to you if I can figure out a faster way. Cool? I don't know. I don't know at this point, but I mean, we did try. We tried our rules. We tried it, and we were able to solve it. Cool. All right. So that's all I got for you today. Quiz next class does not include what we did today. Cool. Quiz next class is just integration by parts and basic integration. Cool. All right. Thanks for watching.